We selected fugitive emissions testing for this topic because we think it is an important topic. The negative effects of greenhouse gas emissions have led to reporting requirements for all major greenhouse gas emitters. Because valves are a large source of emissions in oil refineries, and because the refinery sector is one of the top greenhouse gas emission sources in the US, the pressure to design and qualify valves according to low emission service standards has increased. Today we're going to discuss some of the fugitive emissions standardized test procedures for valves. We're also going to discuss safety and quality related challenges associated with fugitive emissions testing and the methods to address them. So I'm going to start going over an agenda of the presentation today. I'd first like to go over an overview of what will be discussed. We're going to start with background information on greenhouse gas emissions. I'll go over where these emissions occur throughout oil and gas production and go over the EPA's greenhouse gas reporting system. Then I'm going to discuss the current largest greenhouse gas emitters with an emphasis on the refinery sector. I'll break down refineries further to see the main sources of emissions within refineries. And this background information summarizes the driving force behind fugitive emissions testing and why we are qualifying process valves. Next, we'll go over some standard valve qualification procedures for process valves, including the test requirements, placement of instrumentation, general test stand design, maximum allowable leakage requirements, and the leakage measurement methods. And finally, we'll discuss the safety and quality related challenges associated with fugitive emissions testing. I'll provide suggestions on how to address these challenges to ensure safety of the test operators and high quality data to accurately qualify the valve. As Angel mentioned, the presentation will last about 50 minutes, and if you have any questions, you can see Angel's email address is on the top right of the slides. So let's start talking about the threat of greenhouse gases. What are greenhouse gases? These are gases that trap heat in the atmosphere, including carbon dioxide, methane, nitrous oxide, and fluorinated gases. So why do they matter? Well, those greenhouse gases that don't occur naturally from Earth's processes can alter Earth's natural systems, resulting in global warming and climate change. The Earth's average temperature has risen 1.5 degrees Fahrenheit since 1880. This results in high sea level due to melting ice near the poles. It also results in climate change that can lead to stronger hurricanes, increased flooding, and more droughts that fuel massive wildfire outbreaks. Animal species are going extinct at faster rates than ever before, up to 1,000 times faster, according to the International Union for Conservation of Nature. And ozone gases damage ecosystems, creating respiratory health problems and harming crops. Now, how strongly these gases affect the climate change depend on the gas concentration, how long the gases remain in the atmosphere, and the global warming potential of the gases, which is how strongly they absorb energy. Higher global warming potential means to more energy absorption by the gases. Greenhouse gases that don't occur naturally occur through human activity such as burning fossil fuels or producing oil and gas. Now, emissions occur throughout oil and gas production, from onshore and offshore oil wells to the end users, from extraction through production, transport, and even use. The EPA categorizes emissions in different sectors of the U.S. economy. Many of the reported emissions from oil and gas production are categorized in the petroleum and natural gas sector. This includes onshore wells, offshore wells, natural gas boosting and gathering plants, natural gas processing plants, natural gas transmission compression plants, liquefied natural gas storage, liquefied natural gas import and export equipment, and local natural gas distribution companies. However, not all the reported emissions are categorized in the petroleum and natural gas sector. Many of these processes have emissions that are categorized differently, such as under chemicals, electricity generation, or industrial waste. And there are several steps along the production process that don't report direct emissions, but instead the quantity of CO2 that would be emitted if fuels produced, imported, or exported were combusted, released to atmosphere, or oxidized. This includes petroleum product suppliers, natural gas liquids fractionators, and local distribution companies. But the focus for valve fugitive emissions is the refinery sector. Refineries report all crude oil, petroleum products, and natural gas liquids that enter the refinery for processing, so all of the imports. They also report all of the direct emissions from refinery-specific processes. The greenhouse gas emissions from each sector are summed up in reports required by the Greenhouse Gas Reporting Program, or GHGRP. The EPA's GHGRP program is directed by Congress to collect annual greenhouse gas info from top emitting sectors of the U.S. economy. In fact, the EPA has an online tool called FLIGHT, and that stands for Facility Level Information on Greenhouse Gases tool, and it's available to the public with data on over 8,000 emitters of greenhouse gases, and it even lists the company names, where they're located, and their current reported emissions. Apparently, it's now even smartphone friendly, so you can get emission data even easier than you ever have before. The online tool has many neat interactive ways to display the data in pie, bar, and line charts, and you can also filter the emitters if you're looking for a particular industry or location or a particular company. Now, the data presented in this graph is current data as of August 2018, and the unit of measurement is million metric tons of carbon dioxide equivalent. The little e on the end stands for equivalent, and this unit is calculated by multiplying the metric tons of gas by the global warming potential of the gas. That way you can compare different types of gases and not just look at CO2 emissions. The highest emitter was the power plant sector at 1972 million metric tons of CO2 equivalent, followed by 235 for petroleum and natural gas systems, 175 for refineries, and close to 177 for chemicals. Now, the refineries is the fourth largest overall, but if you look at it as one source, the refineries is really the second, because petroleum and natural gas systems and chemicals are made up of a summation of many different processes. Now, if we look at the metric of total emissions per emitter, and this is found by dividing the total number of emissions by the total number of emitters in that industry, we see power plants with 1.31 and refineries second at 1.23, with petroleum and natural gas systems much, much lower at 0.13. And that's because there are way less refinery emitters that report than there are emitters in the petroleum and natural gas sector, 144 compared to 2,253. So consequently, refineries are a large source of greenhouse gas emissions in the U.S., and it's important to minimize these emissions. We know that they are large emitters, but what are the sources at refineries? We have stationary fuel combustion, venting procedures, flares, and fugitive emissions. And if you look at fugitive emissions more closely, you see that valves are the highest emission source at 408 tons per year, followed by connectors at 201 tons per year, and pumps are much lower at only 19 tons per year. This data comes from an EPA publication entitled Protocol for Equipment Leak Emission Estimates. Now, of these four sources at refineries, fugitive emissions is the source that's completely unnecessary. So I think it's important to look at these more closely. What are fugitive emissions? Fugitive emissions are gases or vapor leaks from pressurized industrial equipment. The leaks are not good for air pollution and climate change. They're also not good for the health of the workers in refineries or the local community that lives next to the refineries. Additionally, the process gases are flammable, so if you have increased fugitive emissions, you're increasing the risk of site explosion. I think we can all agree that fugitive emissions are bad news and we need to minimize them. Fugitive emissions can come from any equipment, but today we're focusing on valves. And there's, interestingly, actually been some movement towards a standardized procedure for qualifying gaskets for fugitive emissions testing. But like I said, we'll focus on valves for today. So here is an image of a valve, and it shows the typical fugitive emission areas. You have the body seals, such as the flange joint between the valve body and bonnet. Also the end flanges on the valve that connect to the process pipeline. These areas must be checked for emissions, but they are static seals, so they typically have lower leakage than a stem seal. The stem seal is the primary leak path because it is a dynamic seal. The stem will move up and down during operation, transmitting linear motion from the actuating device to the wedge or the disc that's permitting or preventing flow. And typically, these are sealed with a packing in the bonnet, but that packing will wear over time at extreme pressures and temperatures. There's also thermal expansion and contraction due to fluctuations in temperature that can increase leakage. Additionally, movement of the stem allows foreign particles and debris to move into the packing area, which can impact the wear rate on the packing as well as the ability to seal. So all of these considerations must be taken into effect while designing process valves for refineries. It's not enough to say that a valve was designed for low emissions based on CFD or sound engineering judgment. The risk is too great to assume that they will work for low emissions. So instead, let's put the valves to the test, recreate process conditions, and measure external leakage. And that's where the standardized test procedures for qualification come in. In order to lower emissions and meet requirements from the EPA or from local and state government authorities, end users want to install valves qualified for low emission service at their refineries. But there has to be some type of industry recognized standard to follow when qualifying the valves, or else any valve manufacturer could come up with a procedure, stamp their valve good to go, and there would be no consistency between test methods or passing criteria. So end users specify standardized fugitive emission procedures that they must qualify their valves to in order to install them. These standards are written and approved by representatives from end users, valve manufacturers, packing manufacturers, and test facilities. This approach promotes a broad range of expertise, and it keeps any one company from writing the standard to their advantage. Comments can also be submitted by anyone in the general public. So whether you're a voting member or not, you can submit a comment to the task force, and the task force is obligated to address it and respond to you. The most common standardized procedures for fugitive emissions testing are ISO 15848-1 and -2 and API 624 and 641. And there are also some specific publications by end users with their own criteria, but they're generally pretty similar to these, maybe a bit more restrictive. So starting with ISO 15848-1, this is a standard for measurement, test, and qualification procedures for fugitive emissions. And the -1 denotes that it is for type testing of valves. Type testing is where you test a particular valve design, and once it's qualified, that qualification can be extended to untested valve sizes and classes of the same design if you meet certain conditions, which will be defined in the standards. The test fluid for ISO 15848-1 is helium or methane. The pressure is the pressure rating of the valve at temperature. The temperatures can range from -320 degrees up to 752 degrees Fahrenheit, and this depends on the qualification range of the valve. Now, if you were to qualify a valve from -320 to 750, you would split this up into a complete qualification from room temperature to high temperature, followed by a full qualification from room temperature to -320. You wouldn't go straight from the cold to the hot. The number of thermal cycles for this test ranges from 2 to 4, depending on the endurance class. And the number of mechanical cycles ranges from 205 to 100,000 cycles, depending on the endurance class and also whether the valve is intended for actuation and service as a control valve, or if it's an isolation valve that will remain closed or open for the majority of the operation. Obviously, control valves are intended to be actuated, so they must undergo significantly more mechanical cycles to qualify. And the external leakage measurement methods for this standard are either a combination of the vacuum method, the accumulation or bagging method, and the sniffing method. ISO 15848-2 is very similar, but it's -2, it's the second part, and it's production testing of the valves. So this is where you take one valve from a production lot per valve type, class, and size, and you're qualifying that individual valve, not testing the design. It's a requirement that all the valves tested are already qualified to ISO 15848-1. And this test is much simpler than the first part of the standard. You use helium test gas at low pressures. There's no thermal cycles. There's only 5 mechanical cycles, and you use the sniffing method to detect leakage. The same general procedures are seen in the API FE test standards, but there are some notable differences. API 624 is type testing of rising stem valves equipped with graphite packing for fugitive emissions. The test fluid is methane gas and methane gas only, and this is a notable difference between the ISO standards. The standard references method 21, which is a leak check method established by the EPA for performing fugitive emissions testing, and it requires leakage measurement as a concentration in parts per million. Because of this, and because the procedures do not include a correlation between leak rate and sniff concentration, or between helium and methane test fluids, methane has been selected as the only approved gas for fugitive emissions testing, and this is a heavily debated topic. Testing with methane lowers the maximum test pressure to 600 psi, or the pressure rating of the valve if it's lower than that. It also lowers the temperature to 500 degrees Fahrenheit, and this puts some distance between the test temperature and the auto ignition temperature of methane, which is around 1100 degrees Fahrenheit. The standard requires 3 thermal cycles and 310 mechanical cycles, and the only approved leak detection method is sniffing since the leakage is a concentration, not a leak rate. API 641 is very similar to 624, but it's written for testing of quarter turn valves. The test pressure is defined based on the valve group in the standard, but it is a bit lower than 624 with a minimum of only 100 psi. And it also includes more mechanical cycles than 624 with 610. The test standards have specific instructions on where to place the thermocouples for temperature measurement during testing. The first temperature reading is on the stuffing box by the stem seal. This is the primary temperature measurement point for API 624 testing, and it's used for information purposes as a reference measurement for the ISO standards. The second thermocouple is placed on the valve body exterior, and this is required by both ISO and API as a reference measurement. The third thermocouple is not required by 624 or 641, but it is required for the ISO standards, and it must be installed in the flow path. Now, technically, the thermocouple I have shown on the screen now is in the flow path, but it's best practice to extend the thermocouple probe all the way into the internals of the valve as close as possible to the closure member. It's also good practice to have a room temperature measurement, getting your ambient temperature, and this is a required measurement for some of the specific end user specs. So what does a test stand look like for fugitive emissions testing? Here is a typical setup. You have your thermocouples placed on the valve, like we just discussed. You have a pressure transducer upstream to measure the gas pressure being applied on the valve. A positive displacement pump can be used to pump up the source gas to your target pressure, and that can be with helium or methane. We have an isolation valve installed downstream of the valve, which will be closed so you can build up pressure in the valve. Now, you could also just have a blind flange on the end, but make sure whatever you're testing to doesn't require a through leakage measurement, or else you can install a valve and open it as needed with a mass flow meter to get your through leakage. The coil that's shown upstream of the valve is intended to go inside the thermal enclosure, and this helps lower or raise the gas before entering the valve. And thermal control isn't shown on this P&ID, but the entire valve assembly will need to be enclosed to bring the valve to temperature during thermal cycles, with the actuator outside of the enclosure. We have a PSV, which is a pressure safety valve, installed upstream of the valve, and this protects against overpressurization. Make sure you consider the rating of the valve, the rating of all other components whenever you're selecting the PSV set pressure. And the diagram shown here assumes that this valve would be an air-actuated valve, so you need an air line running to it, with a 3-way valve so you can remotely control the cycles of the valve, and also a pressure transducer that can be used to measure the torque required to actuate the valve during testing. Now, if you were to qualify another valve at the same time, you could have a setup like the one shown here, assuming that you have similar thermal requirements, and that way you can heat and cool them simultaneously, which will speed up time. But you need to be able to isolate each valve from the pressure source and pressurize them independently, which is why we have our automated isolation valves upstream of each valve. Um, if not, then it's going to be hard to determine where the leakage is coming from if you have elevated backgrounds and which valve is actually leaking. Also, I added another PSV for the second valve, assuming it has a different pressure rating. If it didn't, you could plumb both of them together. And this second valve is plumbed assuming that it's a double acting actuator. So you would need to apply air pressure on both sides, and you would need to measure pressure on both sides for your opening and closing torque measurements. So we've discussed pressure and temperature instrumentation, but now I'm going to switch gears to perhaps the most critical measurement, which is external leakage. First, let's discuss external leakage requirements defined by the standards, and then we'll talk about the methods for how to measure them. For ISO 15848-1 and -2, the allowable leakage from body seals is 50 parts per million by volume. This max allowable does not include leakage from the end flanges, but it's good practice to measure this leakage so it doesn't affect other readings. For the API standards, the static and dynamic stem seal, body bonnet connection, and auxiliary valve body connections must all be sniffed, and the leakage requirement for all of these is 100 parts per million by volume. Again, those end flanges aren't required, but it's good practice so that you can make sure it's not affecting the readings that do matter. Now, the ISO test standards, they have different requirements for stem leakage compared to body leakage. So for ISO 15848-1, the allowable stem seal leakage is broken up into different tightness classes. A is the most restrictive and C is the least restrictive. The allowable leakage for methane testing ranges from 50 parts per million by volume to 500 parts per million by volume. But for testing with helium, the allowable stem seal leakage is defined as a measured flow rate, not a concentration. The unit is defined as mass flow rate per stem perimeter length. Therefore, the allowable leakage will increase for valves with larger stem diameters. Again, there are three classes depending on the measured rate, with AH being 10 to the negative 5 milligrams per second per meter, and CH 10 to the negative 2 milligrams per second per meter. The stem seal leakage requirements in ISO 15848-2 are also broken up into three tightness classes, but these are defined as a concentration, ranging from 50 parts per million by volume for Class A to 200 parts per million by volume for Class C. Now that we've discussed the maximum acceptable external leakage to qualify the valves, let's discuss the different methods for measuring external leakage. ISO 15848-1 accepts two methods for measuring the stem seal leakage, the vacuum method and the accumulation method. The vacuum method is shown in this schematic, and it's used with helium gas only and a helium mass spectrometer to measure leakage. Using this method, the leakage source, which includes the body bonnet joint and the stem seal, is enclosed in a tight chamber. The chamber is evacuated and connected to the mass spectrometer, and it must be tight enough to pull a vacuum on the volume, which promotes accurate leakage measurement. The chamber can't interfere with valve actuation, or else you're going to have problems doing your mechanical cycles, and it can be removed during thermal cycling if needed to avoid overheating. The operator must check the vacuum tap running to the mass spec is positioned correctly, and they also must make sure that nothing's clogging the line that runs to the mass spec. Another method is the bagging method. It's also known as the accumulation or suck-through method, and it involves enclosing the valve leakage source in a bagged volume that's also connected to a helium mass spectrometer. But the difference between this and the vacuum method is that, shown in item 4 here, you have a balancing tube that's connected to open air, and it's located on the bag volume, which allows air to enter the volume and mix with the leakage stream. Then the entire gas mixture passes to the sniffer for rate measurement. ISO 15848-1 requires this balance line diameter to be at least 50 times the inside diameter of the sniffer probe. The bag must be tight enough to warrant accurate measurement, and it also cannot interfere with actuation of the valve. The last method is the sniffing method, and this is used by API standards, ISO standards, and EPA Method 21 to measure leakage. The instrument detector probe sniffs the local emission around the stem and body seals. While measuring, it's important to keep the probe as close as possible to the leak source. A helium mass spectrometer or another type of instrument may be used for testing with helium. It's important to consider weather effects if you're using this method because high winds can affect your reading. You want a calm environment. Also, it's important to consider temperature stability because the vapor pressure will increase at increasing temperatures, and this can affect your concentration measurement. So up to this point, we've established the importance of fugitive emissions testing, and we've identified the standardized procedures that can be used to qualify the valves. The next part of the presentation is going to focus on challenges associated with these procedures and some of the methods that we use to address them. The two main focus points for performing fugitive emissions testing, or really any testing, are safety and quality. These procedures involve high temperatures and potentially high pressures depending on the valve pressure rating. We've had test requests up to 15,000 psi at 750 degrees Fahrenheit. So obviously the test procedure poses significant safety hazards, and they must be considered to protect the test operator and avoid equipment damage. Now, quality is a bit more of an abstract concept, but it basically ensures that you've taken the proper steps to acquire accurate data. You're testing at realistic conditions to mimic field application, and you're using a reliable data acquisition system with unbiased measurements. If you don't consider data quality, then the qualification of the valve is inconclusive because your leakage, your pressure, your temperature measurements are not accurate. And there's a bit of an overlap here as well because quality-driven testing promotes a safe test environment. So let's look at some of these safety and quality considerations and how to address them. The main takeaway that I have for safety is that you want to plan ahead. Safety should not be an afterthought. Many of the risks and the associated controls to mitigate those risks greatly affect your test setup. If you procrastinate and you ignore the safety risks until testing begins, you're either going to have an incident or you're going to have a schedule delay as you put the appropriate controls in place. The first safety consideration for fugitive emissions are the high test pressures. As I just mentioned, we've been asked to qualify up to 15,000 psi, and since gas is compressible, the amount of stored energy in the valve, especially large valves, is extremely high. So let's go over some methods we have put in place to mitigate the risk of a pressure-related safety incident. All of our fugitive emissions testing is conducted in a high-pressure test cell designed to prevent structural failures following a significant blast that's caused by high test pressures. So we don't intend to blow things up in these high pressure cells, but if it were to happen, the cell would absorb the impact, and the intent is to protect personnel in the area from tool and fragment hazards that could fly at them. The test cell design required a very thorough analysis, including computational fluid dynamics and prediction of projectile motion to predict the blast loads due to sudden valve failure that would cause a blind flange or another piece of tubing to become a projectile. The walls of the cell contain a 1-inch thick steel plate and horizontal stiffeners, and they were designed to absorb the impacts of an 11-pound bull plug pressurized to 30,000 psi with nitrogen gas. During fugitive emissions testing, personnel are not allowed in the test cell whenever a valve is applied with pressure. In order to keep personnel out of the cell, that means we need remote valve actuation. So we do use remotely controlled valves and pumps to apply the fluid pressure. And if you have pneumatically cycled valves, then you also need automated valves on the air lines running to the actuator so that the mechanical cycles can be controlled remotely as well. All of the components on the setup must be rated for the test pressures. And keep in mind that you're going to temperature extremes and the components will be derated at high temperatures. We also use pressure safety valves, or PSVs, to relieve pressure in case of overpressurization. I would recommend verifying the set pressure of the PSVs by actually testing the PSV prior to performing your fugitive emissions test, and be mindful of the placement of the PSV with the outlet pointing away from sensitive equipment or areas with personnel traffic. Here's an image of a valve we have set up in one of our high pressure test cells for fugitive emissions testing. The panel behind the valve includes a high pressure positive displacement pump that the operator uses to apply pressure safely away from the control room. Another hazard associated with fugitive emissions testing are the extreme temperatures. Temperatures range from cryogenic temperatures that require liquid nitrogen cooling up to 750 degrees Fahrenheit or higher, really, depending on the qualification range. To address this concern, you want to make sure, again, all of your plumbing components are rated for the temperatures. You want to wear the proper PPE whenever you're handling liquid nitrogen or approaching the valve for leak testing measurements. I would recommend safety glasses, a face shield, gloves that cover a majority of the arms, and long sleeves. And make sure that the gloves you select are designated for thermal protection. Just like how we want to isolate operators from high pressures, we want to do the same for high or low temperatures. So remote valve actuation and mechanical cycling is key. The more time you put into setting up the data acquisition system and controls, the less hands-on work for the operator during the test, and thus less exposure to safety risks. The area should be clearly blocked off so that you notify operators working nearby, and you want to post warning signs around the setup that provide the temperature range. The valve shown here was tested to cryogenic temperatures, but some temperatures aren't so obvious from the outside what kind of extremes you're at, so it's really important to notify people nearby. I would also suggest becoming familiar with the safety data sheets of any insulating materials you're using, because many of these will irritate the skin or the lungs if inhaled. Now here's a picture of a valve setup that we have for low temperature thermal cycling. The liquid nitrogen source feeds the environmental controller, and this controls the valve temperature and keeps it near the target temp. The valve in this picture, you can't see it because it's enclosed in the insulation box. The last safety hazard that I want to discuss is the flammable test fluid. If you're testing with methane flashpoint temperature is really low, and so you're constantly off-gassing flammable vapors. To minimize safety risks of working with methane, the testing should be conducted in a well-ventilated area with outdoor testing preferred. Non-rated electronic devices should not be allowed within 15 feet of flammable gas and vapor sources. This includes cell phones, cameras, and non-rated instrumentation. All the electronics that are on the test stand must be approved as intrinsically safe with a minimum of Class 1 Division 2 hazardous area rating. This ensures the equipment will not produce sparks that could ignite the vapors. The test area should be clearly marked with warning signs that indicate the presence of flammable gases. Because the 15-foot rule is hard to visualize, I would recommend putting up a fence or some kind of a barrier around the test stand to keep non-rated electronics out of the space. And the warning signs placed along the barrier should indicate no smoking or hot work nearby. Lastly, portable methane detectors should be worn by personnel entering the space to detect when methane vapors are present. Now this image shows a very large recirculating methane loop we have here at SWRI, and it was designed for gas lift valve testing at very high pressures up to 15,000 psi and temperatures of 250 degrees. But I included it because this facility is a very good example of what you should do when you're working with flammable gases and what kind of safety precautions should be taken. This facility has strict access rules, and it also has a bunch of safety controls that are automated in the data acquisition system. Now, the fugitive emission setup is obviously not near as extensive as that one, but it should follow the same general practice of being performed in a well-ventilated space within a fenced-in area and isolated from all non-rated electrical equipment. The fenced-in area shown to the right here is where we perform our fugitive emissions testing with methane to API standards. Now, switching gears from safety, let's discuss the quality-driven considerations for fugitive emissions testing. The main takeaway here is that data quality matters. Data quality is what determines whether the testing itself was a success or a failure, because without quality data, you cannot accurately conclude whether or not the valve had leakage below the maximum allowable leakage. SWRI has an internal quality system with compliance to API Q1 and ISO 17025. This quality compliance began because we are licensed by API to perform qualification testing on subsurface safety valves according to API 14A and 6AV1 standards. We've actually been licensed to do this for over 40 years now. And in 2013, we expanded our quality system scope to include all third-party testing, including fugitive emissions testing. Our internal quality program ensures all of our testing is conducted with attention given to data quality. Now, regarding fugitive emissions testing specifically, we need to make sure that we consider the accuracy of our pressure and temperature measurements. I would carefully review the accuracy requirements defined in the standards for pressure and temperature. And when you're hitting your target temperatures and pressures, keep in mind the allowable deviation that's included in the standards, and keep in mind the accuracy of your instruments in that deviation, because this is going to narrow your deviation band, but if you know it ahead of time, it'll help you ensure compliance to the standard. Also consider the range of your measuring instrument and the decrease in accuracy as you get close to the low end of that range. You want to select instruments that are ranged appropriately for what you expect to measure during the test. And provide controls to avoid overranging your instruments, because these can also damage them and affect your reading accuracy. And part of our internal quality system is keeping an instrument calibration database, and it has records of all of our instrument calibrations. The accuracy of the instrument should be determined based on the measured accuracy during calibration, not the accuracy that's stated by the instrument manufacturer, because this is typically exaggerated, and we see very large difference between the stated accuracy and the actual accuracy, even with brand new instruments. The instruments should be calibrated at regular intervals, and I would recommend a maximum of 3 months for pressure transducers and 6 months for thermocouples or temperature transducers. However, if an instrument starts looking like it's near the end of its accuracy band, you should increase your calibration frequency. And really, the best practice is to calibrate instruments before and after each test, even if it's still within the calibration window. That way, if something comes back out of range, you can immediately notify the valve manufacturer. Make sure you review the standards and you place all of your instrument sensors correctly, especially with the thermocouple placement that we discussed earlier. I would also suggest using additional instrumentation as references. You will already have reference measurements for temperature if you follow the standard correctly, but think about adding an extra pressure transmitter to the stand as well. We typically have one just downstream of our high pressure pump as a reference measurement. This will help give you an indication if something is not scaled correctly, if an instrument is damaged, or if noise sources in the lab are interfering with the signal. It's easier to take steps to resolve these issues early on instead of midway through the test sequence, so you don't have to repeat cycles. Now, the external leakage measurement is the most critical measurement taken during testing. It determines if the valve will pass or fail the qualification. So this measurement must be accurate, and if not, you have a huge quality concern. The standard procedures define many requirements for the leakage instrumentation, calibration, and operation during testing. Review these procedures carefully when selecting your leakage measurement equipment and performing the test. The standards will list requirements for the leakage detector, including the maximum response time, maximum recovery time, sample flow rate at the detector probe, and the maximum allowable variation or sensitivity of the instrument. Make sure the leak detector is calibrated over the tightness range that you are expecting, and this is especially true for the ISO testing since the tightness class can vary based on the qualification range. The standards also require daily leak calibrations of the mass spectrometer or the methane detector with a calibrated leak. Typically, you can get calibrated leak standards with a valid calibration certificate from the rental company of the gas detector. and make sure you keep a record of these daily calibrations. Lastly, it's critical to determine the response time of the instrument to detect a leak, so the proper duration is used during testing, or else you may miss leaks. The response time is defined as the time between when the calibrated leak standard is opened and the moment when the reading of the instrument shows an increase in helium or methane. The standards have requirements for how long you need to wait during testing to detect leakage once you establish this response time. And for helium testing, when you're using the bagging or the vacuum method, we like to run our tubing lengths all the way outside of our cell to further isolate operators from the safety hazards. So it's important to consider the length of the tubing run that you have going over to the mass spec probe. The response time must be checked by pulling through the entire length of tubing just as it will be installed during testing. Now, the last quality consideration I want to discuss is the possibility of saturating your background with test gas. Background readings must be recorded during testing, and elevated background readings above standard atmospheric levels should return to normal before proceeding with the test. If you get an elevated background reading and finding and fixing the source of the leak is difficult, it can significantly delay your testing. One way to help prevent elevated backgrounds is to minimize the number of threaded MPT fittings that you use on your test stand. MPT threads are the worst for leaks, especially testing with gases. So one spot that we noticed frequent leaks from was actually the end flanges that are connected directly to the valve being qualified. We switched from drilling and tapping the flanges and using MPT threads to drilling a straight hole through the blind flange and then welding a tube fitting to it, and this helped tremendously. Before testing begins, make sure you leak test the stand plumbing and tighten any leaky connections. This will help keep your background low during testing and ensure the measured leaks are coming from the test article, not the stand itself. And be cautious when testing multiple valves simultaneously. You're going to have an increase in your plumbing components, and that's going to lead to more potential leak sources that can saturate your background. And you also need to be able to apply pressure independently to each valve to know which valve has an elevated leak concentration. Just remember that elevated backgrounds do not always indicate valve leakage. It could be from anywhere on the stand, so it's important to minimize the potential leak paths. Well, I hope that this presentation has provided you with a thorough overview of test procedures, best practices, and motivation behind fugitive emissions testing. I'd like to leave you with a few closing remarks. Air pollution, climate change, and health effects drive the need to reduce greenhouse gas emissions. Valves must be qualified and tested to prove compliance to low emission requirements. The standardized test procedures define many requirements for how to conduct the testing, and there are differences between each of them. So make sure you read them carefully and avoid any nonconformances. Mitigating safety concerns is of utmost importance to ensure your operators go home safely each day. So consider safety early in the stages of designing the test stand and not as an afterthought. And lastly, testing is a success only when high quality data is obtained. So put in the effort to ensure accurate, high quality data, or else you won't really benefit from conducting the testing. Thank you for your attention.